Hello, this is the PlayStation to Atari 5200 devlog. I'm Hex. How you doing? It is September 13th, 2010, and today I'm going to talk about a few things. First of all, I'm going to start off with a demo of the digital pots on the adapter. Right now I've just got the adapter held in reset, so it's just stuck at wherever I left it before, and I've got a little meter, and when I take it out of reset, it's going to incrementally just start at about 4K and then just work its way up in roughly 3 to 4K increments every second, and work its way from there. This was kind of a quick demo just to kind of so I could check out the pots and make sure that they were behaving well when I was communicating with them. The way I've got this rigged up is there are 4 of these digital pot IC chips, and each one has 2 pots. In the interest of keeping the time that it takes for me to update all of those pots, I do it in essentially 2 transaction sets. They communicate over an I2C bus, and essentially, instead of just having 4 devices on a single bus, which is how it's typically done, I actually have 1 device on each bus, and then they share a unified clock. So this essentially chops my update time by about 1/4 of what it would take, so it would be 8 transactions versus 2. Not so bad. And the idea there is that I don't want the interval between the PlayStation controller being read and the processing of the adapter and then the final output being presented to the 5200. I want that interval to be as short as possible between that read and this write. And there is still a calculation I need to perform to make that translation for the pot so they can actually do their job. And I haven't worked out how long that's going to take. I'm estimating conservatively that I want to have 10 milliseconds to get all of that done, and everything will be fine. And because a PlayStation controller, it essentially pulls the controller at about a rate of 60 hertz. So 100 hertz, which is 10 milliseconds translated out 1 over frequency, that should be more than adequate to meet that criteria, and it'll also make the response time of the controller work out nicely for the user, hopefully, the user. So that's that. Let me set this aside. So that's that. The other thing I wanted to go back and talk about is the connector, and you may remember this from last episode. And so there's the connector, and you see I've kind of added this snakeskin flex material to it, and I've just kind of slipped this on. Let me slip it into something more comfortable. Yeah, that sounded real appetizing, didn't it? But anyway, I found this stuff on a PC power supply, and I'd seen this used at my old job, and it's pretty good stuff. It's kind of like a Chinese finger trap, if you've ever seen one of those. It comes in great big links, and it's all just a black nylon. So there, my finger got trapped. This stuff is relatively inexpensive. It also gives the cabling a bit more of a professional look, especially if I have this all the way scrunched up on the end like that, and then I can actually clamp that in. So I'll actually, when I do this formally, I'll pull this clamp up, feed this through so it clamps down on this end and then also on this end, so that it'll be flexible. The cables won't get separated. It has some level of security, so you're not gonna wreck this as easily. So it's kind of like, it's better than heat shrink, which was actually what I was thinking about doing for sleeving these cables up. I wanted some way to protect it, and this is actually a lot cheaper too. I think I guesstimated these to be, I don't even remember anymore. It was under $1 a foot, I think, and I was going to buy a 100-foot length. The other thing is I finally got around, I finished cutting that Dalco connector apart. You can see how it's potted up in white, and this was just not going to work out, and why. Just wanted to share that since I had the opportunity to deal with it. The other thing I wanted to catch up on was somebody had asked me about the serial snooper project, and I just kind of did a quick, literally I just sketched it by hand, a block diagram of the snooper and what it does. So you take an input of either RS-232 or RS-422, it's also 488 compatible, and it goes into the device, and then the switches select what mode it supports. So if I put it in one position, it's RS-232, and in the other position it's 422, 488, and then this other switch does the same thing. One position is 232, one position is 488, 422, and it just passes through. So I can actually have this do level translation, so I could have 232 go in and 488, 422 coming out, or any other combination. And then these are RS-232, and it's just taking the transmit and receive signals that are going through and just sending those to another PC essentially, and you can then monitor the traffic that's passing through this snooper. And that's it. It was just a simple debugging tool, and I thought, since at least one person asked the question, I thought it was at least grounds for a little bit of clarification. So hopefully that helps there. Lastly, I wanted to talk about just a general architecture of this design and how it's going to be done. So I've actually got two block diagrams here, and I'm too silly, I just don't know how to make slides and get it on YouTube, so pardon my lack of technical expertise with the internet. So big top level diagram is, here's a 5200, here's the adapter, that dude, here's just a stock 5200 controller or numeric keypad, and really I'm just pulling as a pass through the numeric keypad, and so it's going into the 5200. So 0 through 9, star and pound are actually the only things that pass through here. The fire buttons and the analog, the actual mechanical pots will be ignored essentially. I'm just using it so I can have a keypad. PlayStation controller, pretty straightforward there. And then here's a kind of the next layer down of the adapter. So here are my 4 digital pot ICs, 10K and 1 meg, and so what I've done is I've strung digital pot 10K, the 10K digital pot number 1 in series with the 1 meg digital pot number 3, and so that forms 1 meg plus 10K as a maximum resistance, and the same thing with everybody else here. So there's essentially 4 big resistors, and with essentially 2 taps per axis. And then the digitally controlled analog switches, those are those 74 4066 ICs I was talking about before. They have, I just did a meter measurement with it, and they turn out to be roughly about 60 ohms when turned on, and just an open circuit when turned off. I couldn't find a leakage current or at least some equivalent resistance, probably without blowing it up or something, but it wasn't worth it. Since the carbon dots and the flex pads, or the flex circuit, I'm sorry, and the carbon dot configuration, they spec it out to be around 500 ohms. We're in great shape there. 8051 microcontroller does all my heavy lifting as far as interfacing stuff, and it'll have to do some calculations to translate the values I get from the PlayStation controller into meaningful values for these digital pots. That's going to be very exciting to plan out. The NVRAM is essentially my EEPROM, and hopefully I won't need all of this space that I've got, and if I need more, I have plans on how to deal with that problem. Right now it's going to be just for some stock settings and user configurable settings and a serial number. So essentially each one of these will get a little serial number loaded into it, so we can make sure we know who gets what, and also it'll help me if we start doing numbers of these things. I can actually track revisions and so forth. LCD display, pretty straightforward, I'd think. The user controls up, down, and select is, I was initially going to use just 3 buttons to do this, and I changed my mind. I located a nice cache of momentary toggle switches that are double throw, so I can essentially move, have one position be up and then it would latch, just temporarily be there and then come down to a neutral position, and the other position being down, and it would then come back. So essentially the switch would then be up and down, and then just the push button for the reset, and that'll also be a nice cost saver there. And I think it'll work out overall in terms of usability. As far as user settings, I was actually talking to someone recently, and they had made the suggestion that I was going to do a ideal default settings and save them in the EEPROM, and he actually suggested that I have multiple default settings, where essentially the idea being have 3 or 4 configurations cover 80 or 90% of the user's needs, and then if they still aren't happy, then they can tweak it manually and that gets saved. And I thought that was a great idea, because one thing that I've been concerned about in terms of usability is when I did some bench tests, the Atari 5200 had a set of behavior, and that 4-port I was taking bench measurements on had a certain midpoint and a certain maximum resistance. And I then took another 5200, completely separate system, and hooked it up and tried to get the same numbers out of it and results, and it was nowhere near it. It just, the center had shifted and the maximum resistance had shifted. And so based on that, I had to make the assumption that no two 5200s would be the same, and to make that assumption might be dangerous and would actually reduce usability. So that's why there's this number of digital pots. This gives me the resolution I need. These are all 256 tap potentiometers, and so the 1 megohm, it works out to be roughly like 3.9K per increment, and the 10K, it's 39 ohms per increment. And so I can pretty much get myself anywhere I want to be in terms of resistance presented to the console. But the moving target of the maximum resistance has really made this an interesting effort, and that's the main reason I chose to have the non-volatile RAM, is to compensate for that in a way, because I would assume unless you've got like a big cache of these things, you're going to have one machine set up in your house, and you're going to plug this adapter in, and you're going to be off to the races. And you set it up once and you want to forget about it. You don't want to think about, well, gee, I want to do something else, I need to reconfigure the thing, and I don't want it to forget its settings every time you lose power, because you have to turn the thing off to change the cartridges. So yeah, the EEPROM is definitely the way to go there. Lastly, anyone who has any questions about anything I've talked about in these discussions and these videos, please let me know. This is designed to be an open discussion of this design. I want to produce the best product I can on this, and while there are some things I probably won't budge on, like I'm pretty much married to the 8051 at this point, I'm not going to change my microcontroller just because the PIC is shinier per se. There are better parts out there. Just this is the part I'm used to programming code for, so I used it. But yeah, I'm kind of trying to use this as a form of peer review, as well as a way to let you know, the outside world see what I've been up to and how things are progressing. And as time goes on, and classes are kicking in for me too, so I'm going to be bogged down, and this is probably going to slow down. But the good news is I've got a prototype ready, and I'm down to mostly writing software, which can be a lot easier to deal with, and I can simulate a lot too, so I don't need this hardware present all the time to actually make some headway. So anyway, that's pretty much it. Demo, answers questions, architecture, and if you have any other questions, definitely feel free to leave me a comment or send me an email or forum post. Anyway, thank you very much.